The talks are being sent out also on Zoom. There's a suggestion from the organizers that we wait till 12:15 for the talk. Okay, so we will wait till 12:15. So you have 20 minutes to entertain yourselves. So we'll be starting in a minute.
Right? Yeah, yeah, no. This. Okay.
It's mic. Both for mic will capture and the sound will come.
Okay. And this is for the slides. Oh, okay.
You can walk a bit, not too much.
Okay.
Okay, so 25 minutes.
Okay. This is mic on?
Yes.
Or is- Okay.
So just check with the pointer works. I mean, not.
Yeah. It looks.
Okay. Welcome to session B8. As you saw, there was the first talk. Unfortunately, the speaker was supposed to join online, but we could not get a response. So we have the second talk. So this is on additive word complexity and walnut by Pierre Popoli, Jeffrey Shalit, and Manan Stupulansi. And we have Pierre to present.
Thank you very much. So hi everyone. Thank you for the organizer for organizing this conference. So today we talk about additive word complexity and walnuts. This is a joint work with Jeffrey Shalit and Manon Stipulanti also in the University of Liège. And I will start with a short introduction of my research field, that is the combinatorics on words. So we start with an alphabet. So this is a finite set of symbols, and we call these symbols letters. And with those letters, we will construct words. So these are a finite or infinite list of letters chosen in the alphabet. So we can make finite words, for example, 0, 1, 0, etc. Or we could also make a right infinite word. We will denote epsilon the empty word. So this is the only word of length 0. And so there is a direct correspondence between the words and sequences. So maybe in the future, we say sequences instead of words, but it's okay. There is the natural non-commutative operation on words. It is the concatenation. So if I concatenate AB and BA, and I have the word AB, BA, so this is non-commutative. And then the set A star with the concatenation is a monoid. And on this monoid, we have morphisms. So there are maps that preserve the concatenation. So in the combinatorics on words, we study a lot of different words. And the first word we study are the automatic sequences. So these are words that are generated with a finite automaton. So I will just give a more precise definition later. But for example, this one is the automaton that produced the famous Tremor sequence. So 0, 1, 1, 0, 1, 0, 0, 1, etc. And we also have an algebraic arithmetic definition. So the nth term of this sequence is the sum of digits function base 2 modulus 2. We also have words that are the Sturman words. So we draw a line with an irrational slope. And each time we see a vertical line, we write a 0. And each time we see an horizontal line, we write a 1. And these produce an infinite word. So for instance, this is the famous Fibonacci word. So the slope is the golden mean minus 1. And there is a lot of equivalent definitions for these kind of words and beautiful properties. So they are very, very famous in combinatorics on words. But we also have words with other constructions. So for instance, the Champollion word. So how we construct this one, we concatenate all the binary expansion of integer. So 0, 1, 1, 0, 1, 1, etc. And this produces a binary infinite word, and we will see some properties of this word after. And we also have some strange words like the Kolakowski word. So this is the fixed point of its own run length encoding. So when I have one, I write the number of consecutive values. So 1, the next value is 2, so I write a 1. Then there is 2, 2, so I write a 2, etc. And word is the fixed point of this operation. Oh, sorry. Okay. And what kind of properties we study in combinatorics on words? So this dates from the works of Toué in 1906. And he proved in a very simple way that every word of length larger than 4 over a binary alphabet should contain a square. This is a block of the form XX for word X. So this is done simply by this tree. And after this, he constructs an infinite word avoiding square of a three-letter alphabet. And we will see some properties of this word after. So this is called the variant of Tumor's word. And after this, now the combinatorics on words is the research field that study properties of words with tools of many or various fields like combinatorics, number theory, group theory. And of course, it appears naturally in automata theory and informal languages. So the idea is generally to count something in the word. So it could be specific patterns like frequency of letters, factors, palindrome, etc. We can also counting words with a specific property, words that avoid the pattern, like the squares that we have seen before. And there is also a lot of result on transcendence theory and number theory and stuff like this. So I will now define more precisely what are the main objects of this work that are the automatic sequence. So we start with an abstract numeration system. So this is a triple L, A, and total order. When L is an infinite regular language. So for instance, on the left, we have the classical two numeration language when every word is every binary word is accepted. And on the right, we have another abstract numeration system where there is no two consecutive ones in the representation of integers. So this is why on the right we have 0, 1, 1, 0, 1, 0, 0, etc. And then we say that the sequence is automatic if there exists an automaton that when the output of the automaton, when the input is a representation of an integer in this numeration system, is exactly the nth term of the sequence. So on the left, we have the automaton for the true-Morse sequence. And on the right, this is the automaton for the Fibonacci word, the Sturman word. We can generalize, there is a correspondence between these automatic sequence and morphic sequences that are fixed point of morphism. So morphism, I said it conserves the concatenation. If every word is, if every image is of length 1, we call the morphism encoding. And the morphic sequence is the fixed point order encoding of a morphism. So this right X is a J of F W of A, when FW of A is an infinite fixed point of the morphism starting by A. And we have a famous result of Rigaud and Mass that say that a word is morphic if and only if it's automatic for some abstract numeration system. And in fact, this proof is constructive. So if I give you the morphism, I can construct the numeration system. So in the future, I will sometimes speak about fixed point of morphism or sometimes by U automatic sequences, but keep in mind that this is the same thing. And then we can generalize a bit the notion of automatic sequence by a synchronizing sequence. So a sequence is said to be synchronized if there is a DFA that recognizes the language of n and x of n in parallel. So for example, this is the sequence of odious numbers. So these are the numbers such that the sum of digits in base 2 is odd. And so there is this is the automaton. So just a quick example. So for example, this pair of words is we just follow the arrows, and then this pair of words is accepted. So this means that the 6 terms of this sequence is 13. And in fact, you can check that odious numbers are 1, 2, 4, 7, etc. Another generalization is regular sequences. So sequence is said to be regular if it admits a linear representation. So this is a system of a column vector, a row, lambda, row vector gamma, and the matrix valued morphism mu, such that the n value of the sequence is computed by this product of matrices. And we just give a short example. So for example, the sum of digits function S2 of n satisfies these two easy relation. And then we can provide the following linear representation and how we can compute the sum of digits of 13, for example. So this is lambda times mu1, mu1, mu0, mu1. And this is give the value of 3. So this is another generalization of automatic sequence because we have the following theorem. So automatic sequence implies synchronized, that implies regular, but regular and finitely many values implies automatic. Okay. And so now I will talk about the additive complexity, which is the main complexity we study in the paper. So first I will start with the factor complexity. So a factor of a word is one of the contiguous subblocks. So for example, the word in blue and the word in orange are factors of this infinite word. And then for a given word, we define ln of x, the set of all possible factors of length n that appears in the word. And then we count the number of these n factors, and we call this the factor complexity. So we have some famous results. So the first one is the Morse-Edlund theorem that states that a word is periodic if and only if this complexity is bounded. And we can also prove that almost all words satisfy that they have the full subword complexity. So this second theorem can be used to state that the factor complexity is a measure of pseudo-randomness. And for the family of words that we have studied, so the Sturmian words, so they are the binary aperiodic words with the smallest possible complexity, so n+1. And we have a famous result of Cobham that states that k automatic words are the subword complexity at most linear. And for the Champollion sequence, this is an example of the sequence with a full subword complexity. We can study another complexity. There is a lot more. So, for example, there is the abelian complexity. So we say that two words are abelian equivalent if one is the permutation of the letter of the others. So 0, 1, 0 is abelian equivalent to 1, 0, 0, etc. And then we define the abelian complexity to be the factor complexity up to abelian equivalence. And we have also a characterization of words that have a bounded abelian complexity. These are the family of C-balanced words. And this was proved by Rishon, Sari, and Zamboni in 2011. So there is a lot more complexity, but I will not give so much detail. And now we will study the additive complexity. So for this complexity, we should have an alphabet of natural numbers. And then we say that two words are additively equivalent if the sum of the letters is the same. So 0, 2, 0 is additively equivalent to 1, 0, 1, but they are not abelian equivalent. And then we define the same by the same way this complexity. And since the abelian complexity implies since the abelian equivalence implies the additive equivalence, then the additive complexity is smaller than the abelian complexity. Over an alphabet of 2 letters, this is easy to see that the abelian and the additive equivalents are the same. So we will study only words over alphabet of 3 letters. And also something that is not very common in our research field is that it depends on the values of the letters. And we will see that we will play with this after. So for the abelian complexity, there is a huge literature, but for the additive complexity, there is only 2 results that we have found. So the first one is a result of Ardal, Brown, Djudjic, and Saras Raboudé in 2012. They proved that if the additive complexity is bounded, then there is an additive k power for every k. See, this is a word x1 to xk such that every xi are additively equivalent. In fact, there is the same result for the abelian complexity. And then the second word is just one example by Chen, Wen, and Wu in 2019. They studied the fixed point of this morphism, and they proved that the exact value of the additive complexity. And there is a more general conjecture by Parot, Rigaud, Roland, and Vendôme. The conjecture is to suppose that the abelian or the additive complexity of any U automatic sequence is in fact U regular sequence. And we will see that our theorem is just a specific case of this conjecture. So our first result that we obtain is that if you suppose that we have an automatic sequence in an abstract numeration system, we suppose that the additive complexity is bounded, and this is not very restrictive because we will have an automatic sequence for the additive complexity. But we also suppose that the Parix vector of length n prefixes are synchronized. So this is the most restrictive hypothesis. then we have proved that the additive complexity is in fact automatic, and we can also provide the automaton that computes it. So the Parric vectors, for any word, we have a word of length, vector of length k, which are the number of occurrences of each letter in the word. And as a first application of this theorem, we have a family of morphism. So a morphism is called Parric collinear if the Parric vectors of the image of the morphism are collinear. And in this framework, we have a result from Rigaud, Stipulanti, and Whiteland recently that proved that in this case, then we have exactly the second condition that we need, that are the sequences of prefixes are synchronized for a specific value k. And so we can apply this family of morphism to our theorem, and we can prove that if we have the fixed point of a Parric collinear morphism, then we can compute the additive complexity by a DFO. So I will give just a short example. So let's, for instance, consider the morphism 0 goes to 0, 1, 2, 1 goes to 1, 1, 2, 0, 0, 2, and 2 goes to the empty word. Then we have the fixed point is like this. And then we can compute the two automaton for the abelian complexity and the additive complexity. So if you look to the automaton, in fact, this is very easy to prove that these complexity are in fact periodic. And this was done with a walnut and the semi-group trip, but we just explained it after. What kind of word we can study? So we need a word, a famous word on three letters, so we can think in the Fibonacci word. This is a very famous word in our field. So this is the fixed point of this morphism. 0 goes to 0, 1, 1 goes to 0, 2, and 2 goes to 0. And in fact, this word is an epi-Sturmian word. So this is a generalization of Sturmian word because this factor complexity is 2n plus 1. And this is related to the Fibonacci numeration system. So this is also a kind of generalization of Fibonacci numbers when Tn plus 3 is the sum of the three terms before. And the good news is that this is also supported by walnut. The abelian complexity of this word was already studied in 2010 by Rishom, Sari, and Zamboni, and they proved that this abelian complexity is bounded, and it only takes value in the set 3 to 7. In fact, they prove a little bit more. They prove that for the value 3 and 7, these values are taken infinitely often. And this was the remaining value were studied by Turek in 2013. They proved that also the value cat 4, 5, and 6 are also taken infinitely often. And the main idea to prove this is to find an infinitic parametric family with a constant abelian value. This result was reproved by Shalit in 2021 with walnut, and it proved that actually there is an automaton that computes the abelian complexity of this word. So this was already proved by Turek in 2013, but this is 25 pages of calculus. And with the second proof of Shalit, this is done automatically with walnut. So this is much more easy. And we have also studied the additive complexity for this word. So we have proved that the additive complexity for this word takes only the value in the set 3, 4, 5, and there is a 76 state Fibonacci DFO that computes it. So these are the comparison of the abelian complexity and the additive complexity. And we also done it with walnut and the semi-group trick. One more example. So this is the generalization of the 2-Emers word over 3 letters because we have the fixed point of this sequence satisfied that the nth value is the sum of digits in base 3 modulo 3. The abelian complexity was already determined by Caboret and Cantiagar, and we have proved that the additive complexity have almost the same behavior. So there is 2 possible proof. One by hand. This is not so difficult because you just have to check every form of the factor of length n. But you can also do it by walnut, and this is much more simpler. One last example is the example in the introduction. So the square free words over 3 letters. So this is the fixed point of this morphism. 0 goes to 0, 1, 2, 1 to 0, 2, and 2 to 1. This word was the abelian complexity of this word was already studied by Blanchet, Sadric, Curie, Rampersad, and Fox, and they proved that this complexity is not bounded. and is a big O of log n. And so we wanted to study the additive complexity for this word. And we have something like this. So we suspect that there is a much simpler result for the additive complexity. And in fact, we proved that the additive complexity of this word is only 1 and 3 value all the time. So for this proof, we do not use walnut because it was very, very easy, but we will see other results for this word after. So this example proved that sometimes there is a huge difference between the abelian complexity and the additive complexity. So now I say a few words how to use Walnut. So Walnut is a free software that allows to automatically decide some properties in combinatorics on words. In fact, many of properties that we have seen can be phrased in first order logic. So for instance, the Fibonacci word, so this is the things point of this word, and we see that the syntax of Walnut is very easy. So I can give the morphism to Walnut like this. This we create an automaton that compute this word. And then if you want to have the access to the nth value of this word, this is not so difficult to see this equivalence. So we need only access to the last bit in the representation, the Fibonacci representation of n, and the last bit of the shift, of the right shift, to deduce the value. So this automaton will track the last bit in the Fibonacci representation. If I want to have an automaton for the shift, so this is the function RST, right shift Fibonacci. It takes m and n, and it accepts if and only if n is a right shift of m. So you can check that this works, and then you can check you can compute the number of a specific letter in a prefix of length n. For instance, the number of 0 in the prefix of length n in the Fibonacci word can be computed like this. And then after you can compute the number of 0 in any factor. So like this. So you can you can subtract, but you can use this little trick to. So the number that we are looking for is s. So this is s is the number of 0 in the factor. So I look for the number of 0 in the prefix of length I plus n, and I subtract it to the number of 0 in the factor of the prefix of length I. Okay. And now I want to compute the additive equivalence of two factors. So this can be done like this. So if P is the number of 1, if the factor starting at position I of length n, and Q the number of 2, and R the number of 1 in the factor of length j, starting at j, then I ask to P plus 2 times Q is equal to R plus 2 times S. So this can be done in Walnut, but here we are in some sense lucky because this step was not so long in our example. But this is, if you take a random example, so many times it never ends because it requires too much memory. And then we can obtain a linear representation of the additive complexity also in Walnut. So this provides a linear representation of length of size 184, and just with an algorithm of minimization, it reduced to length 62. And then we only know that the additive complexity is regular, but you can apply an algorithm called the semi-group check algorithm. And because we have this theoretical result of Bestel and Rothenauer that states that if I have a minimal linear representation of regular sequence, then the sequence is in fact automatic if and only if this algorithm stops. I don't give so much detail here, but we just apply this algorithm and hope it will end. But here we knew it will end because the abelian complexity was bounded. And then after the semi-group check, we obtain the famous 76 state automaton. We can also prove that every value is taken infinitely often. So this is very easy, just looking back in the automaton and looking for loops. But you can also ask Walnut if there is infinitely many values for the value of 3. And it returns true every time. So this is proved. Okay, so just to finish, I will just talk about the result when we change the letters. So for example, for the tremors over 3 letters, we change the value 1 and 2 with 1L and M. And so changing the value of letters do not change the abelian complexity, but it can change the additive complexity. And we have proved that, in fact, the additive complexity of this word is the abelian complexity if and only if M is different of 2L, and otherwise we get back to the original case. And this is interesting because we cannot do this with walnut. We can do this on walnut with specific L and M, but not for every L and M. So this was only a combinatorial proof. We also changed the value for the variant of the tremors world. So this was the world with the very simple additive complexity. And we have, so for lambda equal 2, we change only one letter here. So we have a very simple additive complexity. For lambda equals 3 then and 4, it follows the abelian complexity up to the first value. And then we have proved that even if the letter lambda is larger than 5, then the additive complexity is in fact equal to the abelian complexity. And this can be understood that the value 5 is too much large compared to the other letters. And this forces to the additive equivalent factors to be actually abelian equivalent, so to have the same letters. And I will just conclude with open problems. So we have one theorem for that characterize words with a bounded factor complexity. This is the Morse-Edlund theorem. And we also have a theorem for the words with a bounded abelian complexity. So we want maybe to characterize the family of words with bounded additive complexity. So maybe this is difficult because it should depend on the underlying alphabet. And then we have also proved that for balanced words, we can change the value of the letters to have the additive complexity to be equal to the abelian complexity. And so we ask if it's possible to extend the theorem to any word, not just a balanced word. And thank you for your attention.
Questions?
Where is it? Yeah, here. So the idea is to start with just to explore. How can I say this? So you start with the representation of 0, and then you apply every possible label. And then to each new state, you do the same. And if you have already a state that you have already seen, then you create no new states. Okay. So this is a step-by-step algorithm. And if it's done, then there is a finite number of states. And so your sequence is in fact automatic. So you construct your automaton step by step and you hope that it will end.
Yes. So where do the semi group in this?
The semi group is on the, so we just get back to the definition of linear representation. So you compute every value of lambda times mu of the matrices, and this form a semi group.
Any other questions?
On the definition of additive complexity,
Yes.
is the so you're yeah.
Yes.
So you're adding the symbols of your word, right?
Yes.
And so is it standard addition over integer, or does it work with a monoid or a group?
Sorry, I didn't understand.
Is the addition on the letters, is it the standard addition over integers, or does it
Yes.
work with a larger structure like a monoid or a group? Like if I wanted to have a different addition over defined in a custom way over a set of letters.
I don't know any works when the addition is not the standard one. But...
Okay.
Thank you for the question.
Any more questions? Okay, thank you.
Thank you.
So we break for lunch, and reminder that there is magic over lunch.